For 4 billion years, a rock sat quietly in the ground. Dull, reddish-brown, heavy, completely unremarkable. Farmers stepped over it without a glance. Children kicked it aside on their way to play. Builders tossed it into walls just to fill gaps. Nobody looked twice because it looked like nothing at all. Just dirt pressed hard, indistinguishable from the earth around it. And yet buried inside that plain stone was a material that would one day hold up the tallest towers on the planet, carry freight across continents, and form the machines that would pull entire civilizations out of poverty. But you're not just going to learn how humans eventually found iron. You're going to see how an ancient person with no chemistry, no periodic table, no university, could stare at a dull red stone and somehow, through fire, accident, and thousands of failed attempts, pull metal out of it. And strangely enough, the story doesn't begin underground. It begins in the sky. Picture the world before iron. For nearly 2 million years, your ancestors built their entire technology out of stone. Flint, obsidian, quartzite, sharp enough to cut meat, but brittle. One hard strike against bone, and the edge shattered for good. There was no fixing a broken stone tool, it was simply finished. Then, around 5,000 years ago, something changed. People in the Middle East and the Eastern Mediterranean discovered that certain greenish rocks, when placed in a hot enough fire, would release a shining liquid metal. Copper. It could be hammered thin, poured into molds, sharpened again and again. But copper alone is soft. It bends before it cuts. So metalworkers made a second discovery. Mix copper with a small amount of tin, and you get something far tougher. Bronze. Bronze ruled for close to 2,000 years. Bronze swords, bronze plows. The first cities, the first writing systems, the first empires, all of it depended on an alloy that needed 2 separate ingredients. And that was the catch. Tin is rare. It only exists in a handful of places on Earth. Parts of Britain, Central Europe, Central Asia. So for the great civilizations of Egypt, Mesopotamia, and the Aegean, keeping bronze flowing meant maintaining trade routes stretching thousands of miles. Ships hauled tin from Cornwall through the Mediterranean. Caravans dragged it overland from Afghanistan. One collapsed alliance, one sunk fleet. And an empire could lose its most important resource overnight. Meanwhile, an element that could solve this entire problem was sitting beneath every one of their feet. Iron makes up more than 5% of the Earth's crust. It's in the mountains, the riverbeds. Even the reddish clay soil under your own shoes owes its color to iron oxide. There is almost nowhere on the planet where iron ore doesn't exist nearby. And yet, the same civilizations that built pyramids and wrote legal codes couldn't do a single useful thing with it. Here's why. Iron almost never appears as a pure metal in nature. Unlike gold, which sits as shining nuggets in riverbeds, iron reacts violently with oxygen. Over geological time, any exposed iron rusts. It transforms back into dull reddish stone. So, when ancient people looked at iron ore, they weren't looking at hidden treasure. They were looking at rock. Because as far as their world could tell them, it was rock. There was exactly one exception, and it fell from space. Nickel-iron meteorites. Fragments from the cores of shattered asteroids occasionally survived the trip through the atmosphere and landed on Earth already in pure metallic form. These objects behaved nothing like ordinary stone. They were dense, magnetic. When struck, they dented instead of shattering. Ancient people who found them knew immediately they'd found something otherworldly. In ancient Egypt, the word for iron translated literally to metal from heaven. This wasn't poetry. It was an accurate description of the only iron the Egyptians had ever seen. Sumerian texts used a term meaning metal from beyond the sky. Hittite records called it the black iron of the sky. Cultures separated by thousands of miles arrived at the exact same conclusion, independently. Archaeologists have found the proof. In an Egyptian cemetery dating back roughly 3,200 years before the Common Era, 9 small iron beads were recovered, hammered from a fallen meteorite. And in the tomb of Tutankhamun, buried around 1,300 years before the Common Era, a dagger was found with a blade forged from meteoric iron, its nickel content matching known space rock almost perfectly. The boy king was buried with a knife made from the sky. During this era, iron was worth up to 40 times its weight in silver. It sat in royal treasuries beside gold and jewels. But this sky iron wasn't the iron that would remake civilization. That required something else entirely. A fire hot enough to unlock what was buried in ordinary ground rock. Here's the obstacle that delayed everything for centuries. Bronze melts around 950 degrees Celsius, something Bronze Age kilns could easily achieve. But pure iron doesn't melt until you reach roughly 1,538 degrees. That 400-degree gap wasn't a small technical hurdle. It was an entirely different category of problem. When early metalworkers tossed iron-rich rock into their copper furnaces expecting liquid metal, nothing happened. It just sat there, red hot, stubbornly solid. Every sign pointed to one conclusion. This rock was useless. The breakthrough wasn't a single discovery. It accumulated slowly, generation after generation, through people who had no idea where their tinkering was leading. First came charcoal, which burns hotter and cleaner than raw wood. Then came taller, enclosed furnaces, which pulled in stronger drafts of air the way a chimney does. Then came bellows, leather pumps that forced air directly into the fire, pushing furnace temperatures past 1,200 degrees. None of these innovations were designed with iron in mind. They were simply attempts to smelt copper more efficiently, but together they created something nobody had intended, a furnace capable of a reaction no one understood yet. Here's what actually happened inside that fire. At those extreme temperatures, burning charcoal in a partly enclosed space doesn't fully combust. Instead, it produces carbon monoxide, a gas that aggressively strips oxygen from other compounds. As that gas rose through the furnace, it collided with the iron oxide in the ore and pulled the oxygen right out of it, atom by atom. The iron never melted. It transformed in place, solid to solid, from rock into raw metal. What came out wasn't liquid iron pouring into a mold. It was a strange, spongy, porous lump called a bloom. Dark, dull, riddled with trapped slag. When someone pulled it from the ashes expecting nothing useful, they instead held something the world had never seen. Struck with a hammer while hot, it didn't shatter like stone. It bent. It was metal. None of the smelters who figured this out understood chemistry. They had no idea what carbon monoxide was. But through pure observation, the color of the flame, the sound of the bellows, the weight of the ore, they learned to reproduce the process precisely, generation after generation, purely as inherited craft. Turning that spongy bloom into something usable was brutal, physical work. While still nearly white-hot, it was beaten again and again on a stone anvil. Each hammer blow squeezed out trapped slag and fused the iron particles together at a microscopic level, without ever melting them. The result was wrought iron. Tough, bendable, and strong. But there was still a problem. Wrought iron, on its own, was soft. It dulled quickly. Bronze, in its refined form, actually held a sharper edge. The fix came from yet another accident. Blacksmiths noticed that iron left sitting in burning charcoal for long stretches came out different, harder, stiffer. What was happening, though nobody would understand it for another 3,000 years, was that carbon atoms from the charcoal were slowly working their way into the iron's structure. A tiny amount of carbon, under 1% by weight, turned ordinary iron into something new. Steel. Quenched rapidly in cold water, that carbon-rich iron locked into an incredibly hard structure, hard enough to scratch bronze with ease. Blacksmiths didn't know why it worked. They just knew which techniques reliably produced it, and they guarded that knowledge as a craft passed master to apprentice. For centuries after this discovery emerged in Anatolia and the Levant, bronze still dominated. Iron remained a secondary material, until catastrophe struck. Around 1,200 years before the Common Era, in the span of roughly 50 years, the great Bronze Age civilizations of the Eastern Mediterranean collapsed. The Mycenaean palaces fell. The Hittite Empire vanished. Coastal cities burned. And with that collapse, the long trade routes carrying tin fell apart entirely. Bronze became scarce and expensive almost overnight. But iron ore was everywhere, needing no imports, no fragile trade networks, just local rock and a furnace. What might have taken centuries to fully develop under stable conditions was suddenly accelerated by necessity. Communities that had no other choice turned to iron, and over the following generations, blacksmiths refined carburizing and quenching until properly treated steel became 2 to 3 times harder than the finest bronze ever made. And because iron ore existed almost everywhere, this wasn't a technology reserved for kings and palace workshops anymore. A village blacksmith with local ore and a good furnace could outfit an entire community. Iron plows deepened farming into soils that had once resisted cultivation. Iron axes cleared forests into farmland. Ordinary farmers for the first time could own metal tools. Common soldiers could carry metal weapons. Power that had once belonged to a wealthy few began spreading outward, village by village. It's no accident that across the world, blacksmiths were treated as something close to magical. To anyone without an understanding of chemistry, watching someone pull dull rock from the ground, feed it into fire, and produce gleaming, functional metal looked indistinguishable from sorcery. The Greeks gave the world Hephaestus. West African traditions revered Ogun. Norse mythology placed dwarven smiths among the most skilled beings in existence. Different cultures, oceans apart, arrived at the same instinct, that whoever could turn stone into metal held knowledge beyond ordinary human reach. And this story didn't happen just once. In China, furnace technology eventually grew hot enough to fully melt iron, producing cast iron and, by the 1st century of the Common Era, water wheel-powered bellows, a mechanization Europe wouldn't catch up to for over 1,000 years. In India, smiths developed Wootz steel, sealing iron with carbon inside clay crucibles to produce blades so prized they were traded across oceans and later known in the West as Damascus steel. A technique Europe couldn't replicate until the 19th century. In parts of Africa, smelters engineered furnace designs that preheated incoming air for maximum efficiency, arriving independently at engineering principles Europe wouldn't formalize for centuries. Stand in any modern city today and look up. The steel frame holding that skyscraper together, the rebar buried in the concrete beneath your feet, the bridge, the train, the ship, the car. Every gram of it began as dull ore pulled from the ground, run through a furnace where carbon monoxide stripped away oxygen atom by atom, exactly the same reaction that happened inside a clay furnace on an Anatolian hillside 3,000 years ago. The scale has changed by a factor of millions. The chemistry hasn't changed at all. The person who first pulled a bloom from the ashes and discovered that hammering it produced metal had no idea what they had started. They weren't standing at the end of a story about rocks. They were standing at the very beginning of the modern world.